String theory is a theoretical framework that attempts to unify all fundamental forces and particles in nature by describing them as vibrations of tiny, one-dimensional objects known as strings. String theory has emerged as a leading candidate for a theory of everything, as it offers a solution to several long-standing problems in physics. However, it also poses several challenges and conflicts with our current understanding of gravity, which is described by Einstein's general theory of relativity. One of the key features of string theory is its prediction of extra dimensions beyond the familiar three spatial dimensions and one time dimension. In string theory, the universe is assumed to have 10 dimensions, of which 6 are compactified or curled up into tiny spaces too small to be observed directly. The remaining 4 dimensions, 3 spatial dimensions and 1 time dimension, are the ones we experience in our daily lives. These extra dimensions play a crucial role in string theory, as they enable the theory to reconcile quantum mechanics with general relativity. One of the main challenges of reconciling quantum mechanics with general relativity is the so-called problem of quantizing gravity. In quantum mechanics, particles are described by wave functions, which are represented by a complex number known as the wave function amplitude. However, in general relativity, the curvature of spacetime is described by a set of 10 equations known as the Einstein field equations, which are based on the concept of a continuous, smooth manifold. It has proven difficult to reconcile these two descriptions, as the wave functions of quantum mechanics are discrete and discontinuous, whereas the curvature of spacetime in general relativity is continuous and smooth. String theory offers a solution to this problem by introducing the idea of a quantized string. In string theory, particles are no longer point-like objects but are instead represented as tiny strings, which vibrate at different frequencies. The different modes of vibration correspond to different particles and their properties, such as mass and charge. By introducing strings, string theory provides a way to describe gravity in terms of a quantized object, rather than a continuous field, and thus overcomes the problem of quantizing gravity. Another important feature of string theory is its prediction of supersymmetry. Supersymmetry is a theoretical symmetry between particles with integer spin, bosons, and particles with half-integer spin, fermions. In supersymmetric theories, every particle has a superpartner with a different spin. Supersymmetry is a crucial component of string theory because it enables the theory to reconcile the various fundamental forces in nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, unified theory. However, despite its many successes, string theory faces several challenges and conflicts with general relativity. One of the most significant challenges is the so-called landscape problem. String theory predicts the existence of a vast number of possible universes, each with its own set of physical laws and properties. This means that the universe we observe may be just one of many possible universes, and it is unclear why we happen to live in this particular universe. Another challenge is the problem of predicting the correct number of dimensions. String theory predicts that the universe has 10 dimensions, but it is unclear why we only observe 4 dimensions, 3 spatial dimensions and 1 time dimension. Some versions of string theory predict the existence of additional dimensions that are too small to be observed, while others predict the existence of large extra dimensions that could be observed in particle accelerators. However, these predictions have not yet been confirmed by experiment, and it is unclear which version of string theory is correct. Perhaps the most significant conflict between string theory and general relativity is the problem of black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. In general relativity, black holes are described by a set of equations known as the Schwarzschild solution, which predicts that black holes have an event horizon, a boundary beyond which nothing can escape, and a singularity, a point of infinite density and curvature where the laws of physics break down. However, in string theory, the singularity is predicted to be resolved by quantum effects, leading to the prediction of a fuzzball. A fuzzball is a hypothetical object that replaces the singularity in string theory and is thought to be made up of strings and branes. Fuzzballs are non-singular and have no event horizon, meaning that they do not violate the laws of quantum mechanics. This prediction of fuzzballs conflicts with the black hole information paradox, which is a problem that arises when considering the fate of information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but in general relativity, information that falls into a black hole is thought to be lost forever. String theory predicts that the information is encoded on the surface of the fuzzball and is not lost, which would resolve the paradox. However, this prediction is still theoretical and has not yet been experimentally confirmed. Another conflict between string theory and general relativity is the problem of dark energy. Dark energy is a mysterious form of energy that is thought to be responsible for the accelerating expansion of the universe. In general relativity, dark energy is described by the cosmological constant, which is a constant term added to Einstein's field equations to account for the observed acceleration. However, in string theory, the cosmological constant is predicted to be much larger than the observed value, leading to the so-called cosmological constant problem. In summary, string theory is a theoretical framework that attempts to unify all fundamental forces and particles in nature by describing them as vibrations of tiny, one-dimensional objects known as strings. It offers a solution to several long-standing problems in physics, such as the problem of quantizing gravity and the unification of fundamental forces. However, it also poses several challenges and conflicts with our current understanding of gravity, such as the landscape problem, the prediction of extra dimensions, and the problem of black holes and dark energy. Despite these challenges, string theory remains a promising avenue for a theory of everything and continues to be an active area of research in theoretical physics.